Hello everyone. Am I audible? Okay, so good evening. This is my PhD research scholar at Mechanical Engineering Department. Now, if you are not aware, the purpose these kind of sessions are to really help to solve the assignment problem, a detailed discussion of the current week's content, and at the same time discuss some advanced level concepts from the content which you are already taught in the classes, and uh, also because you don't get an exposure to live tutorials in these NPTEL classes platform. So this is the one of kind collaborative MRF, NCC, as well as actually actually help you all as well as gamer scholars for India. So what we will be doing today, because the assignment solution week one and two are not released yet, I suppose. So we will actually be discussing some uh, interesting topics out of week one and week two content. Uh, then uh, we'll actually try to solve starting from basic to some advanced level problems here. May help you solving the assignment questions, as well as if you want some of you are appearing national level, that may help. So we will start. So I hope my screen is visible to all of you. And ahead, uh, I hope such a concept has already been discussed in your regular classes. So now we are going to fields. Supposing you already know what an adhesive, abrasive, and diffusion wear is, there are two kind of uh, encountered wear mechanisms of the uh, processes which we come across in our daily life. One is fatigue wear, one is corrosive wear. Fatigue wear is a kind of wear or machine parts which are subjected to a cyclic kind of loading. What I mean to say is, in process, you can think of some rotating parts within a engine. Then you can think of a pulley, belt and pulley, where parts are subjected to constant cycling loading, maybe 1,000 to exercise days. So there can be such cases, or there can be uh, quite much of tolerances between the surfaces of machine parts. But with time, owing to plastic deformation, parts come in touch and can actually, over time, face a kind of wear which is called as fatigue wear. And same kind of load applied at the same point. This kind of connections or this kind of touch happens, and a fatigue wear is encountered. It's corrosive wear. I think if somebody's mic is on, just switch it off. You don't have a question. Wear. So kind of wears are encountered when the surface is exposed to open air. There can be oxidation on the surface of a part, and owing to that oxidation, surface gets weakened, durableness gets affected, and when that surface comes in contact with another surface, the deformed or affected oxidized surface corrosion may take. So this kind of wears are called as corrosive wears. The question here says which of the following phenomena is correct with respect to mechanical wear? One is abrasion, one is adhesion. So you all know abrasion where happens when hard particles dislodge material from the that happens owing to the ploughing action of one surface over the another. Then there is diffusion wear which happens when a concentration gradient is there. So there is always flow a concentration can also natural phenomena such as cyclone and tornado where concentration gradient of rain droplets or clouds over the sky actually lead of clouds from heavy cloud high pressure to low pressure region where is same kind of concentration gradient actually atoms from one to another and diffusion where then you have addition where we're going to strong and bonds the metals in contact can actually break apart the space and contact. So it is not correct here. Addition options correct because here it says dissimilar.
हेलो हेलो
Yes.
सर वॉइस ले से वॉइस कम आ रहा है वॉइस वॉइस कम आ रहा है वॉइस आवाज
Okay. Okay.
आपका आवाज कम आ रहा है
Okay. अभी आ रहा है?
हाँ अभी थोड़ा थोड़ा बढ़ गया तो अब थोड़ा बढ़ा और
Okay. Okay. So in this case, the option C answer it is not correct with respect to the wear because adhesion wear is something in which when there is a very strong going to very strong atomic bonding one surface when it comes to contact with another actually takes away erodes away some uh, particles from the surface of the
सर
complementary.
अभी भी कम है आवाज
Is this the problem with everybody else? Hello. Anyways, uh, if let's proceed. So this is all about the concept of wear and a little more additions to what you have actually been taught around in the regular classes. We'll move The equilibrium phase diagram. Uh, I think you know already what solidus, liquidus, and solvus lines are. Talking about solidus lines, these are the highest solidus. What is solidus temperature? It is the highest temperature at which the first droplet, liquid droplet, a particular metal is formed. If you look at the diagram, so these kind of lines are called solidus lines. Uh, this is one line, this is one solidus line. So solidus line is actually a partition between a pure solid phase, the solid and liquid phased alloy. And then there is a liquidus line uh, like this, in which actually distinguishes a liquid phase with a liquid and solid phase. For example, here you can see alpha and L. Alpha is a solid phase, L is a liquid phase. Here is beta and L. Beta is a solid phase, L is a liquid. So liquidus is represented by a line on a phase diagram that separates a liquid phase from a solid plus liquid phase. The system must be heated above the liquidus temperature to actually become liquid. So if this point you consider as a partition between the liquid phase and the solid and liquid phases, so up to this temperature, a particular alloy will remain liquid, and then beyond that point, first solid crystal starts forming. So this is called as the liquidus point, and these are just lines. And then you have a solvus. Okay, the solvus is represented by a line on a phase diagram that actually separates a solid phase from two different solid phases. For example, here, this is alpha is a solid phase, alpha plus beta is also a solid phase. So the catch here is the percentage of the component materials. For example, uh, here in case of iron carbon diagram, what happens, the carbon percentage varies along this particular line. So based upon the percentage of carbon or proportion of carbon present in the alloy, there can be variations in the properties that the particular alloy shows. So alpha behaves in a particular way, and alpha plus beta, this phase behaves in a different way. So this kind of line which separates two solid phases but of different compositions called is called a solvus line. Okay, I hope that clears. That too will proceed with uh, a very popular iron carbon phase diagram. The carbon percentage here you can see goes on increasing along the x-axis and along the abscissa from 0 to 6%. And depending upon the percentage of carbon, there are different phases formed, such as perlite, ferrite, cementite, okay, through along this abscissa. So uh, will be actually exposed to questions based on this iron carbon phase diagram in the slides. These points, these liquidus lines, the solidus lines, and these uh, solvus lines. So you have already discussed, and now you know how the varying percentages of carbon can give rise to different phase of alloys, carbon alloys, just perlite, ferrite, and cementite. Okay, there are different key points such as 0.83 percentage carbon. Here you have 0.02 percentage carbon. These things you should keep in mind always to answer questions out of this iron carbon phase diagram. Okay, I think someone is trying to Anyways, we'll continue with our slides. So moving ahead, this is the first question out of the equilibrium phase diagram. Says it asks which of the following is not true for eutectic point in the equilibrium phase diagram. First of all, uh, what are eutectic, eutectoid, and peritectic points? I showed you three different key points in the iron carbon phase diagram. So these are by standard named as eutectic, eutectoid, and peritectic points. So eutectic is where a liquid transforms into two solid phases. For example, for lead and SN group at 183 degrees centigrade, you actually for the first solid crystals are formed out of a liquid, a PBS and alloy. Okay. Similarly, in case of eutectoid, one solid phase actually transforms into two other solid phases. So this is what we were talking about, which is being separated by solvers line. Okay. So here also, for example, in the iron carbon diagram, you can see at 727 degree, check here, you can see at around 727 degree, what happens is uh, this phase, gamma phase, gets converted into pyrite and uh, ferrite phases. So these are called as eutectoid points, and then you have this peritectic point where one liquid and one solid phase actually transform into and solid phase. So same thing you can see in the iron carbon diagram at 1493 degree centigrade. So here this thing happens. Then so just having exposed you to this these phases called eutectic, eutectoid, and peritectic points and different corresponding phases, can you answer me which of the following is not true for eutectic point? The point is where liquid is transformed into an solid phases. The first point says it's the specific composition of two metals which has a specific fusing point. Uh, this is correct, right? And then you have the point where a liquid instantaneously converts into two solid phases. This is by definition correct. It is also called an easy melting point. So that is not kind of right. So option D remains wrong. That all of the above are not correct. All of the above are correct. Okay. And then moving ahead, so let me ask you how much iron does cementite contain? What is cementite? It is Fe3C. And why is it limited to a particular quantity? So the maximum iron, so this is the reason. Okay, so beyond 6.67% of carbon, what happens is, I mean, the extreme right end of the iron phase diagram, iron carbon phase diagram, where it is the maximum carbon percentage at 6.67%, that all the carbon present is cementite and extra carbon in the form of graphite. So what is graphite? You have seen your pencils, right? In the pencil, whatever material is used for you to write is graphite material. Okay. So you can see here the structure of graphite. It is a layered lattice structure. So one particular layer is very strong because of the kind of covalent bonds that they share. But the problem comes up when we go from one layer to another. So there are very weak bonds between two different layers. So individual layers are very strong, but the layers can be separated by just the slightest disturbance because there are no strong covalent bonds between two consecutive layers. So what happens is there is a slip factor that comes up with a single little shear force that you apply. Uh, what is shear force? Shear force is a force which is applied parallel to a particular surface, right? Here, once you apply this kind of shear forces, one layer slips over the other, and Uh, Although each layer is very strong, overall cutting through the material is very easy. Graphite and uh, then becomes very unacceptable to use in structural applications such as automotive or aerospace industries. Okay, so that is the reason that carbon percentage is limited to 6.67 and not extended beyond because of the formation of graphite. Okay, keep such concepts in mind, because such questions may come up in the multiple choice exam also. So now the next topic comes up about these are different kind of elements which are actually named which are topping elements of steel. Like steel is the heart and heart of manufacturing industry. You all know, but uh, depending upon the application where the material is being used, for example, in aerospace or automotive or marine industries or defense sectors, like what do you want out of a particular part? So, uh, whether you want the strength, you want hardenability, you want the high temperature or cryogenic resistance, you want the product to be highly machinable, ductile, tough. Depending upon those things, the steel is doped with different kind of uh, materials like these, and such as chrome, manganese, molybdenum. Molybdenum improves hardenability and high temperature strength. Right. Similarly, what does manganese do? Manganese increases strength of steel and assists with deoxidation. Manganese has a milder effect on strength of steel than carbon. Okay, so given that uh, use of manganese, if you look at these four options, and option D says manganese actually increase ductility. But if manganese increases strength and then cannot simultaneously increase ductility, right? So option D is incorrect. Uh, I will share the slides with you just to go through all those dopants and the corresponding use and applications of those dopants towards the manufacturability and machinability of steel. One you might get one such question in your answer exam. Ahead, which of the following form of iron carbon composition is hard? Some of you answer me. Avinash says martensite. Can you, Avinash, tell me why do you think martensite is actually the hardest? Why not austenite, benite, pearlite? Now, somebody wants to talk, you unmute yourself and you can speak actually. Uh, the other case, so martensite is actually the hardest owing to its grain structure. Now, uh, austenite, you can see above 747 degrees when you actually heat, or so this process is called as tampering, heat tampering. Then austenite starts forming. The first crystal of austenite is formed at around 147 degrees. Now, once austenite is formed, and then now, by the way, do you know what this S curve stands for and how is it formed? The S curve is all actually showing the different kind of uh, uh, alloys being formed at different through the temperature and time. Now, suppose you start cooling down austenite at a particular rate up to uh, somewhere around 650 degree, and then you hold it here for a longer time. What you will see is at this particular time point, benite starts forming, and then if you again cool down austenite up to around 1000 degrees and then hold, immediately see perlite starts forming, right? Similarly, if you rapidly cool down austenite up to this particular temperature range, then we will see that this is, by the way, called quenching, rapid cooling process. The martensite being formed. Now, because you have carried out rapid cooling, what happens is the grains doesn't get enough time to uh, actually relax and recrystallize. By recrystallize, I mean the formation of new crystals from different nucleation sites. So the grains remain small, and this actually leads to the hardness or strength of martensite material. But owing to the high strength and brittleness, martensite is often uh, treated unusable for practical structural applications without any doping. So with the dopants, martensite is often used in structural applications. Answer, where is martensite? And the reason is grain structure, very small grains without recrystallization out of very rapid cooling. Okay. So now moving ahead, Vinash, do you have any question? So is this question available in your assignment, in your assignment, question out of your assignment? I can't directly answer assignment questions here. Um, the I can only discuss once the answers are released. I can only discuss the concepts. I think whatever I have discussed yet is enough This particular question is enough to clarify your doubt. So, did it clarify your doubt, Avinash? So, you have asked one question that at 0.8% carbon, is it perlite or ferrite? So if you look at the iron carbon diagram, if you at this iron carbon diagram, here you can see up to point 8% of carbon content. So the microstructure is considered actually perlite. Okay, because this thing can be actually cleared from the eutectic composition. This is called an eutectic point. Okay, so uh, an eutectic reaction, if you look at eutectic reactions in carbon and carbon phase diagram, you can actually see that at 0.8% carbon composition, the perlite microstructures are being formed. So we were in this question. After that, we come to uh, one question from casting. So there are different kind of allowances in casting. One is a shrinkage allowance. What kind of shrinkage happens to be the maximum? That is solidification shrinkage. The shrinkage that happens when cooling down up to room temperature. So that is called as from freezing to room. That is called as solidification shrinkage, and the allowance which needs to be taken care of during solidification shrinkage is actually called is actually the maximum. The question says determine the pattern to casting volume ratio when there is a requirement 1% shrinkage allowance in pattern making process. So let's take 10 minutes time. Let's try to attend and answer this question. Then I will show you the solution. try and answer this question. We solve it on pen and paper. You can guess it by a simple layer only. Anyways, let me show you the solution. It's very simple. So the question said you have to find out the casting pattern to casting volume ratio. Now, what is a shrinkage allowance? During solidification, the casting volume actually undergoes the shrinkage, right? To encounter that, we are give an allowance early on during the casting process. So the pattern volume must be lower than the casting volume, right? So the ratio of pattern to casting volume must be less than 1. Right? And now, because this is a volumetric platform, so here you have a cube of a dimension, so it must be in the cube. That's a simple way to guess if there are multiple options. And then this is a 1% shrinkage, so that means 0.01, and the pattern volume should be less than the casting volume in order to take care of the shrinkage. So the pattern volume in this case should be 1 minus 0.01 into 100, similarly for all the dimensions. And then the casting volume remains similar, 100, 110. The ratio becomes 0.99 cube.
सर पैटर्न तो बड़ा रहेगा ना पैटर्न.
Pattern doesn't remain, pattern volume should remain small. Otherwise, how can we accommodate the shrinkage?
तो श्रिंकेज में उसका कम हो जाएगा डायमेंशन कास्टिंग का.
Yeah,
श्रिंकेज में उसका कास्टिंग का डायमेंशन कम हो जाएगा ना.
that's why the casting volume, the volume within the casting cavity should be more than the pattern, because
Okay.
it will ultimately come down. So that after the finalized product which you get should be of the required volume. Like if you want one dimension to be of 10 mm, then you make sure that the initial dimension is 10.1 mm. 1 mm you give it for shrinkage, consider for shrinkage. I hope that clarified you. Anyways, so moving ahead, you have one question from gating. You have top gating, bottom gating. There is something called parting line gating. So a gating design is a very important and interesting topic with respect to casting and then with respect to of your evaluation systems. Now, there are advantages and disadvantages of both top and bottom gating, led to researchers of a trade-off between the top and bottom, and then came up the parting line gating. Now, what are the advantages and disadvantages of top gating? So first of all, what is top gating? The molten metal comes up from the top of this screw, then starts filling up from the top, right? So the bottom surface is to ambient atmosphere, and the bottom surface, any metal which comes in contact with the bottom surface gets solidified first, and subsequently layer by layer all the layers goes on solidifying until unless this last level top surface gets solidified. So This is called as a temperature gradient, right? So the first layer which comes in contact with the ambient gets solidified, the temperature comes down. Then the next layer is having a lower, considerably lower temperature because it is again coming in contact with the cool down first layer, and subsequently all the layers are having a increasing temperature with the top layer having the highest temperature, which is the temperature of the molten metal, right? So this kind of gating are called top gating. Just the opposite of that is bottom gating. Comes in from the bottom and starts on filling the mold cavity bottom up. So the gradient here follows just the reverse of what happens in case of top gating. So what are the advantages of top gating? So it happens from top to bottoms under gravity. So the rate is quite high naturally. The cooling rate is quite high naturally. Time taken is less. Then you have favorable thermal gradient because this first layer gets cooled and then the next layer comes in the cool down first. That goes on happening here. Now, what is the problem? The problem is with erosion because the speed is more. The rate of cooling it goes on eroding the wall materials. The eroded materials are also included within the casting, and then this creates some defects in the solidified part later on. Then long height castings. In case of very long height castings, so this kind of top gate gating systems are very unreliable because of very high speed of molten material. Erosion becomes too severe to actually get any favorable. Then the bottom gating, it involves a little much of turbulence and sand erosion. Why? Because the rate is generally slow. Metal is poured bottom up, uh, is against gravity. The speed is low. But the problem is it takes up a lot of time till the same gravity, which is relatively faster at top gating. Now, because of this low speed, the quality of the product, the surface finish, and the length, the products are almost defect free. So, good quality casting surfaces are achieved in case of bottom gating. Okay. Then there is very unfavorable thermal gradient. So, what happens is uh, the hot molten metal comes into the cavity from bottom surface, right? And this is the surface which is connected to ambient. Uh, this is a low temperature surface. Once the high temperature molten metal comes in contact with the low temperature surface, starts solidifying without completely filling up the internal cavity. It takes place at the bottom, it could choke off the material flow before the mold is full. Even before the mold is full, this layer, if gets freezed up, then the inlet port gets choked, and then there will be very big voids and cavities left inside. So that will actually give a very quick product at the end. And then you have this kind of parting gating systems, which is actually a trade-off between the top and bottom, and this actually do take care of the advantages of both and then minimizes the disadvantages of cutting. Line gating is the most used case of casting. Out on this slide. if not, we'll move to the next topic. The next topic is about binary uh, alloy. Okay, again, a topic similar to iron carbon phase diagram. Uh, this will be a question out of a phase diagram of a binary alloy. So the alloy is having 28% by weight of copper and remaining silver Ag, which solidifies at 779 degree. Solid consists of two phases A and B. Okay, both are solid phases. Phase A has 9% copper and B has 8% silver at 779 degree. Now the question is at room temperature when they're pure silver and copper, you have to estimate the amount of solid A and B, the above alloy at 779 degree and at room temperature. The alloy consists of 28% copper and 72% of silver and solidifies at 779 degree. When a particular phase A has 9% copper and 8% silver, at this solidification temperature, you have to find out what amount of A and B uh, are actually there in the particular alloy at that very temperature. So I'll give you the um, diagram, phase diagram for this question to help you out. Just try and solve it. Then I will show you the discuss the solution with you. Are you guys able to find the solution to this problem? Just apply lever rule. I think you have already read about lever rule. Solve these phase diagrams for binary alloys. Simple application of lever rule will give you the answer. And if you can solve this question, you can actually solve 99% of problems out of these diagrams. There was one doubt, I think, in the casting process, the pattern volume is larger than the casting volume because patterns are designed to be slightly bigger than the final casting to account for the shrinkage of the metal as it cools size, meaning the pattern needs extra material to compensate for the contraction during. Right. So I think there is a confusion in that question. So I'll just take you to the question once. So here, what it says is determine the pattern to casting volume. So what here the question means is the pattern is your actual pattern, and this casting volume means casting pattern volume. Okay, like this should be the dimension of the pattern, and this casting volume should be the dimension of your pattern which is uh, desired in order to take care of this shrinkage. Okay, so just don't get confused with this casting volume. So this means casting pattern volume. That way the casting pattern volume should always be larger than the pattern actual pattern volume in order to take care of the shrinkage during solidification. That way the ratio comes less than 1. Anyways, let's come back to this problem. Now can see this diagram where this is the solidus line, this is the solvus line, this is a liquidus line. We have discussed this earlier. Now alpha, actually alpha and beta are two phases here, A and B. These are written A and B here. And this is an alpha solid liquid phase. This is a beta plus liquid phase. These are solid plus both solid phases combination. Okay. Now uh, is this point is A, B, and C, depending on the various composition of copper, or you can alternately say silver, the uh, particular alloy. So silver is 100% here, pure silver, and it goes on reducing as copper goes on increasing and becomes the maximum at 100% at the rightmost point over the abscissa. To simply drop the lines out of these points, changing points, phase changing points, so you can actually get an idea of what is the percentage of copper at that particular point. Okay, says that at 779 is A has 9% copper and B has 8% silver. Okay, so A phase, there is alpha here, has 9% copper. Okay, and it goes on increasing up to the last point where it increases to 100%. Same time, silver is at 8% and go left up to 100%. Okay, so if this diagram is clear, you can simply solve it using lever rule. So 8% of alpha, or A in this case, is given by BC. So BC is nothing but the composition of copper at point C minus the composition of copper at point B. At the solidification point, the composition of copper is 28%. It was given in the question, right? So in that case, BC becomes 92% copper at C minus 28% copper at B when divided by AC is 92% copper and is 9% copper. That way you can find out the weight percent of composition A or alpha. And similarly for B, that happens to be AB by AC. and AB is simply 28% minus 9% of uh, copper divided by 92% of copper minus 9% of copper. Okay, so 76% of uh, A and 24% of B is there in the alloy uh, at that 770 degree temperature. Okay. So after that, you come to the second part. So there is one more question, right? At room temperature also you have to find out. At room temperature, 8% of alpha. What happens at room temperature? At room temperatures, both are pure metals, right? Silver is at 100%, copper is at 100%. So in that case, it becomes BC dash. Okay, these phases are not there, pure metals. So that case, BC dash copper is at 100% at room temperature, minus of 28% at the solidification temperature, and then AC dash. So or A dash C dash. So both A is at 100%, okay, and silver is at zero, right? C dash. Similarly, you can find the weight percent of beta. It comes out to 28%. It was already given. So that way you can solve this question. And now we come to a topic: how many number of atoms. I think it's very easy. You can simply calculate it if you have an idea of how many number of atoms are there in the different kind of cubic cells. So this is SSC, simple cubic, centered and face centered. Case of SSC, you have total of uh, one effective atoms in one cell, right? One cell is shared, one atom is shared by eight cells, eight sides. So you have, for one particular cell, it is 1/8 of one. So if you just take in 1/8 from all different atoms, you just come up to one effective number of atoms. And similarly for BCC, you have this one plus one at the center of the that is two. And in FCC again you have one from all the corner atoms, and base atoms are again shared by two side by side cells. So a total number of six face atoms, each shared by two. So you have 6 into half. So total effectively comes out to be 4. So here it was asked for a BCC crystal structure, and the answer should be 2. Uh, Moving ahead to a very interesting topic, what is called strain hardening. It is a very crucial phenomena which occurs in all the manufacturing processes, and it influences the strength of a material heavily. All the concepts of plastic deformation, ductility, brittleness, everything comes out of somewhere, some way, are being influenced by strain hardening phenomenon. So there are two kind of uh, defects which are technically present during manufacturing processes. One is called edge dislocation, one is called screw dislocation. Okay. So edge dislocation is where defect moves parallel the surface in the line of the defect. Okay. Then in case of screw, it's perpendicular to the that. Okay. So here, if you can visualize a half plane of extra atoms are there present. Okay, so full, then comes on half plane of extra row of atoms, right? So these atoms are again absent in the next half. So this actually is visualized as a dislocation. Now, as and when there is a force from maybe the left, now this plane moves to the right, this moves to the right, this moves to the right. and then this is again pushed away to the right, the extra row of atoms. As long as the extra row of atoms goes and moving to the right, you can simply visualize the left out half plane opposing atoms being pushed to the left. Okay, so both the defect is moving parallel to the direction of force applied, right? So this kind of dislocations are called edge dislocations. And when this happens perpendicular, like you give a force here and the motion happens in this way, this is called a screw dislocation. What happens is whenever there is such kind of dislocation, uh, you go on applying forces, and there are multiple such dislocation defects present in a particular material, a particular part which has been machined. All those dislocations go on piling up over one another, right? So there is one dislocation out of this plane, there can be one from here, okay? Multiple dislocations can actually pile up and then further restrict the movement of this dislocation. Okay. So what happens then, even though the force is being applied, the material dimensions doesn't change as proportional as in proportion to the amount of force applied. So you can see in this graph, somewhere beyond the yield point, what happens is the stress increases more than the strain, right? So if you take out the slope here, you can see uh, the y-axis is always more than the x, right? So the amount of stress the material can hold is more than the amount of strain or deformation that is being actually visible after yield point, right? After the material is already yielded. This comes out of the defects present, and this is called as strain hardening. The material can actually now withstand more stress and we can say the material gets strengthened out of strain hardening process. Okay, uh, is that clear to all? If it is clear, we'll one more question. So here you say you have to find out the ductility percentage. Ductility always is being found out in terms of percentage reduction. Just uh, be mindful of that, and then you have to find the true stress of fracture. Now you have to know what true stress and engineering stress is. So engineering stress is determined based on the original area of a particular part. Okay. And then true stress is found out based on the real-time deformed area. The true stress is a more practical uh, parameter find out the stress acting on a material, but it is difficult to find that out directly. So always find out engine stress, and based on some formulation, we find out the true stress. So try to solve this question. Show the solution in a little while. hope you have tried. The solution is very easy. And at the final dimension of 10.7 and the initial dimension of 12.8 uh, before being fractured as the initial minus final by initial, this reduction area becomes 30%. Then just find stress, find the found by step. You can also simply relation for stress sigma true equal to sigma engineering into one, so that you the actual way to solve other than using the force always remains constant throughout the tensile testing method, right? Force can be found in the area. Sigma F is the fracture stress and K naught is area at the start of the formation or tensile testing process. So you can find the as force T and as to pi axial dimension 8, bring the dia by 2 radius square comes around 59 kilonewton. Then you can find out the stress considering the area, fracture area AF, that you can find out that the 60 megapascal. Yeah, we'll move to the aspect of mechanical engineering. We try to understand what stress strain curves, strain curves vary in case of different types of materials. Okay. First one is a linearly elastic material, which the material only behaves it is a purely perfectly elastic material, and it only uh, uh, it gets fractured beyond the elastic point, and there is no plastic region. Silent, all know. Now there is two concepts to remember here. One is proportionality, one is plastic point up to which the material weighs Hooke's law. And beyond that comes the elastic limit, where after which the uh, proportionality is maintained, elasticity is maintained, but the proportionality is not maintained. Material is elastic, but doesn't obey Hooke's law. That is called elastic limit, which comes beyond proportionality limit. But that comes an elastic, perfectly plastic material. So the material behaves perfectly up to elastic point, and then it comes from the plastic. So this particular region, what are these arrows? Suppose the material has a vent beyond that elastic point, and there you want to actually pull back the material, remove the load, and get the material back to its original point. Does that follow? Is already reached its plastic region of deformation, so it doesn't come back to its original shape and size, right? So whatever you try, there will always be one recovered region. So this part is the recovered region, and one region is which remains unrecovered. This arrow is to show you that the material will never come back to initial undeformed shape. Then you have a linear hardening. We have talked about strain hardening earlier. So instead of following perfect plastic relation. So it will go high. The slope is in a way that the stress material can handle more stress now as compared to the pain, as compared to, you can say, the deformation. Uh, what happens is the material has become stronger. So that is called linear strain hardening. That rigidly perfectly a plastic material, so there is no elastic region. At the start of the load application, the plastically never comes back to the initial point. There is a power law, so this kind of laws are there simply to define materials which are not linearly plastic or linearly elastic. So the this material, this kind of materials where linear hardening is there, but practically linear hardening is hardly found, and power law defines those materials in which linear hardening. A here is the yield point, and 1 by 3 it is called in hardening exponent. Depending upon that exponent, the material undergoes strain hardening, and hence the plastic region is defined. Then you have this kind of viscoelastic materials. So what are exactly viscoelastic materials? The viscoelastic material between liquid and those of elastic solid. Okay, so as like such as polymeric materials, thermoplastic and thermosetting plastics, such okay, so these materials transition quickly undergo transition to liquid phase from solid, right? There is a very narrow margin between solid and liquid phases, and there is one point where these materials can behave both as liquid as well as an elastic solid. Okay. These kind of materials are called as viscoelastic materials. Just kind of just train behaviors of different kind of very that follow the slide, which among the characteristic that a perfect elastic body holds. So and I guess it is completely recovers shape. The deforming follows. Now there is one question that the property of material by which it can be beaten or rolled into thin sheets. A lot of you know that called malleability. But the question is the difference between rigidity and malleability. Elasticity and plasticity you all know by now, but what is the difference between ductility and malleability? Ductile materials can be drawn into wires. Malleable materials can also be drawn into wires, but the issue is that malleable materials uh, offer more resistance towards uh, towards tensile loading, uh, and can be actually beaten into thin sheets and very easier deformed along their thickness. Materials, on the other hand, are offer more compressive resistance. They can be drawn into where their allowability towards tensile deformation. One next question is, how is toughness different from resilience? Same. So toughness and resilience are different depending upon the area of sustain curve which are taken into account. So you can see that the modulus of toughness. Modulus is nothing but simply the toughness divided by its volume, right? Now the modulus of toughness is the amount of strain energy per unit volume, strain energy density that a material can just before it fractures. That is the total energy which the material for fracture point. For ductile fracture, it follows the plastic region. It the plastic region there. Modulus of toughness is calculated as the area under the stress strain curve up to the fracture point, and accurate calculation of the total area under the stress strain curve under toughness is. And what about resilience? The resilience modulus of resilience is strain energy per unit volume, strain energy density. The material can absorb to the permanent deformation. Only up to the elastic point, right? Modulus of resilience is calculated as the area under the stress strain curve up to the elastic limit. However, since the elastic limit and the yield point are typically very close, the resilience approximate area under the stress strain curve up to the yield point. The elastic and the yield points are hardly distinguishable by application. Times modulus of resilience can also be calculated by taking into account area up to the yield point only. I hope you are now well acquainted between the difference of toughness and. For the last topic of today, come to the calculation of edge length of a unit cell, kind of crystal structures. So there can be simple cubic, face centered, body centered, hexagonal. This. How are they calculated? Suppose this is one simple cubic cell. So there are four atoms in corners. If you calculate the edge length, this is very simple. Have to take uh, the you have to simply take half a dia, that is r plus for 1 half into 2 r plus r into 2 r, so that r, right? Get it. Then comes the body centered cubic structure, in which have calculate the APF, atomic packing factor. Before that, and you know how an APF is defined, it is simple volume of atom divided by the volume of unit cell. Calculating uh, the volume of unit cell, you have to, what is the edge length? Consider this green line, one diagonal line running between this corner atom to the top father and corner atom, and there is one between. Okay, the green line. How do you calculate this? This calculate by taking into consideration this blue diagonal on one face first. Right. If you know one edge length is a, by Pythagoras theorem, you can find out the dimension of this line d, which root 2a, right? Square root of 2 multiplied by a. Simply using Pythagoras in this bigger triangle, the green, red, and blue. You know the green one is simply the dimension of these two atoms. That is again rad. So this is half half of 2r, simply as I found out here, half of the dia, and again half of the dia, and then this is one more 2r here. This becomes r, and r for the central atom, so 4r. This is 4r, d you have calculated to be root over of 2 by a, and this dimension is already a. This one, you know, using Pythagoras, you can find out a is 4 by square root of 3 multiplied r, radius of one atom. Simply using a to find, you can find out the volume of the cube. Volume of atom is simply 4 by 3 pi r cube. Atoms per unit cell. We have calculated the effective number of atoms in BCC to be 2. You can find out the volume of atoms, volume of cube, and the ratio to be around 68%. Going ahead to calculate the same for face-centered crystals concept. Now you can find out this dimension to be A, this to be A, and this becomes 4R. As the earlier case, in case of BCC, A in this case by Pythagoras becomes 2 divided by square root 2 multiplied by R. To find out the volume of Q, volume of atoms, it is 4 in this case. Now the total effective number of atoms is 4 in face centered, right? We have seen it earlier. The total volume of atoms becomes 4 into volume of one particular atom, 4 by 3 pi r cube, you know, sphere. So you find the ratio to be 74%. Okay. Similarly, in case of hexagonal prism, you can find out the area of the total surface and then multiply it with the height to find out the volume. Okay. Now, if you consider a hexagon like this, so you know all those triangles are equilateral triangles, right? If you drop a bisector, that should divide the base into half, right? By the property of equilateral triangles. So now, if you know the dimensions of one smaller triangle, you can actually find out the area of this hexagon uh, by uh, this way, half into base into height, so root 3 by 4 square. That you can find out the area of hexagon by multiplying 6 for the six number of triangles, 3 by 2x square. And if you know the area of hexagon, you can multiply this with the height c of the HCP structure to find out the volume of the unit cell. C can be found out to be by 3R. The total volume of the HCP unit cell becomes 24 over 2R cube. So that way, somehow we have touched upon most of the topics or and try to solve some problems which can actually clarify your doubts regarding the assignment questions and further give you some insights on some advanced topics. Some of these topics may also help you in entrance exams such as GATE and outside your graduation. We conclude by this slide. If you have any doubt, uh, it was.
हेलो।
Yeah, tell me.
हेलो।
Yeah, please tell me.
हो गया?
जी जी जी.
नहीं, रिकॉर्डिंग चालू है आपका?
Sorry.
रिकॉर्डिंग चालू है, रिकॉर्डिंग।
हाँ वो ठीक है. If you don't have any questions,
लेफ्ट करो मीटिंग।
yeah yeah yeah.
थैंक यू सर।